Hi everyone, we are talking about Wavelet Trees today, and this is a very interesting topic because it helps you simplify your life when you're answering range queries. Okay, so some of you might be knowing about persistent segment trees, but this is a data structure which you can use to replace PST more often than not. So let's get to it. So initially, as usual, we have an array given to us, and this array is of size 13. You see that the elements are randomly ordered. There's no sorting or anything done yet. Now, what you want to do is find the median of this array, and that will come out to be some value. But just to make things simpler, what I'm going to do is take the smallest value and the largest value in this array and divide that by 2. So I'm going to take the range of elements in this array and just take the middle of that. Okay, that's also a reasonably good way to partition this array into two separate arrays. That's what we're going to do. We're just going to take this array and we're going to partition it into two arrays. So this is something that we call a stable partition. You can have a look in the link below, which is explaining this concept. This stable partition is going to contain all elements less than a particular value v, and this partition is going to contain all elements greater than this particular value v. So this is going to contain less than equal to, and this is going to contain greater than v. Alright. So v in our case is 1 plus, what's the maximum value? Smallest is 1, maximum is 9. So that is 10 by 2. The range of elements is 10 by 2. The middle is going to be 5. So v is 5 for us. And all elements greater than 5 should fall here. All elements less than or equal to 5 will fall here. Okay, so 2 goes here. 1 comes here. 7 goes here. That's nice. 6 goes here. 4 comes here again. 8 is here. Or is it? No. In fact, 8 isn't here, 8 should be going here, after which 9 comes in. Then we have 4, then we have 3, then we have 7, which goes here. So 7 is here, there's 5, which is coming here, after which there's 9. 2 will come back to this array, and finally 7 will fall on this side of the array. So what we are seeing is that the original array has been broken into two parts. This is called a binary partition, and this is a stable partition because you have a particular value 5. All elements to the left of this array, the left partition, have values less than or equal to 5, but the ordering is the same as in the original array. And almost the exact same thing for the right part is that all elements are having value greater than the pivot value, you can say, and the ordering is the same. So we'll go on doing this recursively till the whole tree is completed. So when do you know you have hit a leaf node? When all elements in that particular leaf are the same, right? So let's do that. And so there we have it. We have the Wavelet tree with us. You can see that each of these bracketed numbers are the pivots for that particular parent, and two partitions are coming out of it. Finally, all the leaf nodes are going to be just nodes having one particular value. So 9, 8, 7, 6, so on and so forth. You'll also see that the number of leaf nodes in this Wavelet tree is equal to the number of distinct values that the parent has. I mean, the original array had. So you can see 1, 2, 3, 4, 5, 6, 7, 8, and 9 are the distinct values that this parent has. Also, you see that sometimes the pivot is not a perfect integer. So this is 6.5, this is 8.5, but the logic is the same. Anything less than or equal to the pivot goes to the left, anything greater than that goes to the right. Now there are some very interesting operations that Wavelet trees can do. There's something called rank. So rank is basically finding out the frequency of an element q in the range I to j. Okay, Wavelet trees are really good at this. There's also another thing which is equally interesting, which is called quantile. Right, so what is the kth largest element in a range I to j? Okay, and if you knew this, then you could have solved mkth num without using persistent segment trees. So these two operations are really interesting. There's another operation which is actually even more interesting, which is finding out all elements in the range x to y for the index range I to j. Okay, Wavelet trees can give you this also efficiently. So we'll get to this in the next video, but these two operations are what we are going to start off with. So how do we answer for a range I to j? What is what is the frequency of the element Q in it. Okay, so one interesting thing to know about is Wavelet trees are not just this. They also can tell you another type of query. Given an index I, let's say 6, right? I is equal to 6. The Wavelet tree can tell you how many of the elements up to 0.6 have gone to the left side and how many elements up to 0.6 have gone to the right side. And this is actually quite simple because when you're constructing the Wavelet tree, what you'll do is you come to the very first element 2 and you'll see whether it's falling to the left or to the right partition. So because 2 is less than or equal to 5, it will fall to the left partition. And what you're going to do is say, fine, left partition size plus plus, let's say. So left size plus plus. This is equal to 1 now. When you come at 1, you're going to note this down because up to 1, up to index 1, the number of elements falling to the left is equal to 1. The number of elements falling to the right is equal to 0. When 1 comes in, again you do left size plus plus. And now at 7, you will have number of elements falling to the left side are 2, number of elements falling to the right side are still 0. But at 7, this will of course change. This will become right size plus plus. And so for 6, values will be left size till this point is 2 and right size till this point is 1. So number of elements before 6 falling to the left are 2 and number of elements before 6 falling to the right is 1. So there's this one element greater than 5, right? And of course you can also store 2 other values, which is the smallest element and the largest element based on which you did the partition. So you can store those here. This is 1,9. This will be 6,9 and so on and so forth. So these are pretty simple techniques to find out the number of elements to the left and to the right subtree. Okay, so I need to find the frequency of Q in the range I to J. I can simplify by saying that I need to find the frequency of Q in the range 1 to J minus the frequency of Q in the range 1 to I. So when I'm saying 1 to I, actually it's 0. So because it's 0 indexed, right? So I don't need to have this 0 thing. What I can say is I can define a new function such that it's going to tell me the number of elements having value Q up to a point I from 0. So that's the same here. And in fact, it's not going to be I, it's going to be I minus 1 because you want to take I also into consideration. So I minus 1 and J just here. Alright, this is going to be equal to rank of Q ij. Okay, how do we do this? So as an example, let's take Q equal to 9, I equal to 4 and J equal to 11. So the range is from 4 to 11 and you need to find the occurrences of 9 in this range. You also see that I have drawn a black array that is actually the left index. So all elements up to this point, up to this index, which are falling to the left of the left subtree basically. And right can be calculated, right of I can be calculated as I minus left of I because the total number of elements are the same. So you have the two arrays left and right. You have everything with you. You have the query given. Let's see what happens. So Q is equal to 9. The first thing you need to notice is that this value 9 is greater than the pivot value you have. So you have to go to the right of the given array, right subtree. Another thing you need to notice is this range. So firstly, they're going to pick up number of elements which are equal to 9 up to point J, up to point 11. Where does 11 map to in the right subtree? You're interested in that. So 11 maps to, index 11 maps to 11 minus 6, which is 5. So it maps over here. You see that makes sense. It's this index. What's next? Over here, you'll see that the same query has to be answered, except a little differently. Over here, you'll see that again Q is equal to 9. The partitioning value is 7.5, which is less than 9. So you have to go to the right subtree. And up to this point, you need to find the mapping up to 5. So that will come out to be exactly 2. Okay, so you come here, and again the same thing comes in. 8.5 is less than 9, so you have to map to the right. On the right, you try to find the mapping of 2, index 2, so that will come out to be this index, and therefore you have two values. When you hit a leaf node, you're just going to return whatever index you're at. So you're mapping over here, you return that index. So that is equal to index 1. So total number of elements which are equal to 9 is 2. Okay, let's make it a little more interesting. Let's put this as 8. What will then happen is that, oh no, let's not do that. Let's put this as 9, and let's put j as 10. Okay, so what's happening is basically I got rid of this 9 in this range. So for this query, you have j equal to 10, so that's 10, and you need to map to the right, so that will be minus left of I, which is left of 10, or is it left of something else? If you map to left of 10, you will find out the number of elements which are before it and mapping to the left. What you really want is the number of elements up to this point. So you have to do 10 minus left of 11, right? Which is equal to 10 minus 6, which is 4 elements. And the same thing had happened previously also. I had made the mistake of pointing out the wrong element. When you had j equal to 11, you were actually subtracting with 6 over here, not this one, but this one. The same thing happened here, 10 minus 6, so that gives you 4. That maps to this element here, pointing at 7, okay? Now, we don't have the map left and map right written down over there, but what's going to happen is this element here will map up to this point, because this 9 is excluded, and you can work that out by yourself. But you come here, and again going to the right because you're searching for q equal to 9. So all the time you're going to the right, and you come to this element. Okay, so at this point what you'll see is that the index is equal to 0, meaning that the number of elements is equal to 1. And of course, if you can answer for any arbitrary j, you can answer for any arbitrary I also. So f of j with q minus f of I minus 1 with q is going to give you rank of q in that range I to j. Okay, so this is actually pretty simple compared to the next one, which is quantile k I to j. So what this says is that in the range I to j, if I want the kth smallest element, what is the value of that element? Similar to in I to j, what I'm going to do is I'm going to sort all the elements, and then I'm going to pick up the element with index k. Okay, so this is exactly what mkth num asks you, and we'll solve this now using Wavelet Trees, and it's going to be a more logical solution. So instead of trying to answer for a range I to j, we'll make our life simpler just like last time and say that we want to find the kth largest element from elements 0, index 0, up to the point j. That's what we're going to do for some arbitrary j. Now this is actually very simple, because if I want for a particular index j, I can map to the left and map to the right. So I can map all elements which are fallen to the left of it and all elements which are fallen to the right of it up to this point. Not this point including, but excluding this point. So k, what is the kth largest over there? Well, simply if I find, let's take j equal to 10 again, and let's take k equal to 3. So I want to find the third largest element. Yeah, third largest. So j equal to 10, map left 6, tells me that there's 6 elements which fall to the left up to this point, j. So yeah, all 6 elements fall here. That's great. Really? No. Yeah, 6 elements. So that is from 0 to 5. Makes sense. So from 0 to 5, this is your end range now. Basically, let's just put that down to 6 elements here. Alright. 6 elements fall to the left. You want to find the third largest element. You have 6 elements falling to the left. That means that your third largest element must be amongst these 6 elements. So from your original array, you need to move to the left subarray, and you also need to keep that mapping with you. So till this point you had 10 elements to map. Now you need to move to the element which is being pointed by this index. So that's going to be 6 elements. You can just say 6 minus 1 is going to be its index number, which is going to be 5. It seems like a lot of hocus pocus with the indexing going on, but honestly, it's actually quite simple once you write down the code. So up to this element, we are going to be finding out the third largest element now. Okay, because k is equal to 3. Coming here, we see that 5 is going to be mapped up to this point. Alright, to the right. And from here, it's going to be mapped up to index 2. So 3 elements are to the left. We want the third largest. It has to be to the left. So we go to the left subtree, and now we try to find out up to what point is that mapping being done to the left. 5 is being mapped to index 2, and that's where we go. 2 and 1 are falling to the left of it, and then 3 comes in. So the number of elements falling to the left are just 2. And the number of elements falling to the right now is 1 up to this point. What does that tell you? Well, we are looking for the third largest element. 2 of the elements fall on the left subtree, which means that our element has to exist in the right subtree. So the algorithm is this. If you map to the left and you get a number c, if k is greater than c, go to the right. Otherwise, go to the left. And while you're doing this, constantly go on mapping to the right and map to the left, respectively. Okay, so now finally we're going to the right of the subtree because 2 is less than 3, which is the rank that we're looking at. So we go to the right subtree and we map this index 2 to the right, which is 0. Okay, and once we have come here, we see that it's a leaf node. So you wanted to find the kth largest element in this query. Because it's a leaf node, you can answer whatever element exists in that leaf node. So all elements in the leaf node will be equal. So your answer is 3 for j equal to 10 and k equal to 3. So let's just have a look. From 0 to 10, 1 exists, 1 comes just once, 2 comes just once, and I think 3 is probably the largest element, probably the third largest element, yeah. Where is 3? Oh yeah, 3 exists here. Yeah. So just cross-verifying, you see that in this range, if you sort the elements, you're going to lose out on this 2. 1, 2, and then the third largest element is 3. There's nothing else. This 2 is not going to be included in that range for j equal to 10. And the best thing about this is that this range query from I to j is very similar to the query that we just saw for all elements from 0 to j. So let's take j equal to 10, I equal to 4, and k equal to, let's say the fourth largest element. K equal to 3 gives you the fourth largest element because the index is going to be 3. So from I to j, this point. So what you're going to do is find out the number of elements which are being mapped to the left up to this point, up to index 3. And similarly, all elements up to index 10. So I minus 1. Doing this, you see that 6 is being mapped to 2. 2 elements before 6, including 6, fall to the left. And 6 elements, including 5, fall to the left. So you have 4 elements to the left. So basically that says that your element is being contained in this subarray. So now what we do is map the indexes of these 2 elements to the left subarray because we have 4 elements to the left and we want the fourth largest. So we are going to the left. So this element 4 is going up to this point 2. What about this element? 5 is going up to this point. So you're seeing that there are 4 elements here. Okay, now in this range again, I has become 2, j has become 5, and you're still looking for the fourth largest among these guys. So again, I minus 1 is the range that you want. So I minus 1 up to this point and up to this point. So for this element, where is it being mapped? There are 2 elements to the left here, and there are up to 5, right? There's 3 elements to the left here for these 2. So 3 minus 2 gives you 1. 1 is less than 4. So you need to go to the right. Now, going to the right subtree, you also need to map the two indexes, these two indexes, to the right. So 5 maps itself over here to 5, and this 4 maps itself to this index, 0. Okay. Now, amongst these three, which is the element you're looking for? You're not looking for the fourth largest anymore, because you went to the right, you lost out on one element, so you're looking for the third largest now. Okay. Now our strategy is that for the third largest element, again, map to the left indexes. Where does 4 fall here? It falls at index 0. Where does 5 fall? It falls at index 1. Number of elements here is equal to 2 actually. So you're now looking for the first largest. Or to put things simply, at this point k became 2 and the indexes were 0 to 2. And at this point, we saw that the indexes are 0 and 1. We see that the number of elements, the difference in number of elements is basically 2. So k has suddenly become 0 because you're going to the right subtree here. And now mapping these two elements, you see 4 maps to 0 and 5 also maps to 0. You can directly return the element. And plus it's a leaf node, so yeah. 5 is the element you're looking for. And if you see this range, 4, 8, 9, 4, 3, 7, and 5, and you sort them, that gives you 3, 4, 4, 5. I think 8 and 9 are the only remaining elements. So amongst these, the fourth largest is 5. So that's what we got. Okay, so it's a complicated data structure, no doubt about it. But the thing is, it is simpler than many of the data structures out there for some complicated problems. For example, the problems that we are trying to solve in a range, find me what is the kth largest element. So what I'll do is I'll put a few links in the description below for references and the code. And if you want any notifications for this, you can subscribe. I'll be going deeper into this data structure soon, Wavelet Trees, with updates and lots of other operations that this tree can perform. So until next time then, see you.